Papa Flammy's Advent Calendar.
Here. Good morning, fellow mathematicians. Welcome back to another episode on Papa Flammy's Advent Calendar. And that was the wrong introduction indeed. Today, it's not fellow mathematicians, it's good morning, fellow physicists. We are going to take a look at a little experiment today. One that my students are gonna do on Monday, so tomorrow. So if they are smart and they want to get a good grade, they better take a look at this video today. And the main star of today's video is gonna be this nifty little device. It's called a capacitor. Maybe you have seen it before. Looks like this. It's basically built into everything because what it does, it acts like some kind of battery, just without much of the stuff that you find inside of a battery. It's a very nifty little device and it does work wonders, and it's a really cool device. This is why we are going to cover it. But before we dive in, as always, make sure to use code to get 15% over on my spring shop on everything, and also 10% over on stemmench.com. So check it out and support the channel this way. Now, as always with my experiments and everything, I'm going to hand out a worksheet to my class and they need to work through everything here. And at the end, they are going to write down everything, what they observe and all the other tasks mentioned here. And then they are gonna give it to me and I'm going to create it. It's a bunch of things they have to do. They have 120 minutes to complete all of this. It's a 12th grade. So they are going to get into a bunch of formal physics too. So it's gonna be a lot of fun, I suppose. But before we take a look at the main experiment and the parts that it contains, I would like to at first go over to the blackboard and explain one or two things about this fucking capacitor that I can't get out of here, this wonderful little individual, because some of you might not be familiar with this device. I'm going to explain it to you how I understand it at that point. I'm a bit of a physicist myself, and I hope it does make a bit of sense to you. Let's go, shall we? Now, as mentioned before, this little guy right here is a kind of magical if you really think about it. It's like a battery, so it can store energy, a certain voltage or charge, but without the need of acid, for example, and the like. So what we do with a capacitor is we just put it into a circuit. What you need for the capacitor is just some kind of transformator, or basically a source of electricity, and then you get your capacitor here. The symbol for the capacitor looks like this in the circuit, and we got a plus and a minus pole down here. Now let us close in on this capacitor a tiny little bit and let's see what it consists of. So if we zoom in quite a bit, then a capacitor looks like this. It's a bit different here. If you take a look at that thing, it has an outer casing. It's in fact circular, so it's a disc, a cylinder in some kind of way, but this doesn't take away from the point. Now, the two main parts that a capacitor only consists of are the capacitor plates that we got right here, which are made out of a conducting material, and inside of the capacitor, between those two plates, is a so-called dielectric. It's a non-conducting material. So it could be, for example, air or anything of that sort. Oh, I've never done this to my Hagoromo child. This is not nice. Ugh. Never mind that. So we got a non-conducting material in here, this dielectric, and we got two capacitor plates. And that's about it. That is all that really is in here on a basic level. But how can it store energy if it looks like this? Let me try to explain a tiny little bit, at least how I understand capacitors at this point. Now what you do in a normal case, you take electricity, like with the transformator that I got over here, and then you are going to let a positive charge flow into your circuit. What is going to happen is so-called influence, or I think it's also called outside of Europe induction. I think it's electrostatic induction. The positive charges that we got here are going to attract due to the Coulomb forces that are acting on all the other particles inside of the conducting cable that we got right here, for example. It's gonna attract all the negative charges. So there are a lot of negative charges in here. In a normal case, a cable is neutrally charged, but now it's gonna attract due to this electrostatic influence or induction, all the negative charges in here, and they are gonna be tracked down to the positive pole of your electricity source. Now that also means that in the only case we have a neutral charge here too, so plus and minus, they are neutrally charged. All of those negative charges are going to be drawn out of your capacitor, leaving you with a positive charge on this plate overall. Now the same thing happens due to the induction over on this side. We have a negative charge here, and now all the positive charges are going to be tracked out of our capacitor and gonna be drawn due to the Coulomb forces to the side, and all the negative charges from the electric source away. So into the other plate of the capacitor. What happens in a normal case if you have just a closed circuit? They're just gonna go merry-go-round, so positive goes to minus and so on at all times. But here we are gonna get a charge on our individual plates. Now, if you would have water in here, for example, another conducting material, not distilled water, just regular water, then all the positive charges would flow over to the negative charges, because we have negative charges over here, a majority of those, so the positive charges would like to flow over here. But now we got this dielectric material here, meaning it's kind of blocking the way, you could say. So kind of the entrance to the negative side over here. Now the very interesting thing with a non-conducting material is that we don't have free charges that are rolling around in here. So no charges can flow from this side to the other. But one thing that is very cool about the dielectric is that so-called polarization is going to play a role in here too. Because in normal case you are going to have an electric field in here. It's going to have this direction, for example, if we take the physicist direction from plus to negative. But now, in a dielectric material, in a non-conducting material, we don't have free charges, but what we have are dipoles. And those dipoles, what they are going to do is, they are going to rearrange. The dipoles are looking like this, for example, with a positive and negative charge here. But with a dipole moment, they can turn around inside of the non-conducting material, and we are gonna have a direction of negative and plus like this. So the negative dipole parts are gonna point into the positive direction, and the positive parts into the negative direction. And this is gonna be inside of the whole material. Now what is gonna happen if we have this situation is that in a normal case we have an overwhelming electric field, which is gonna act on the other plate. In a normal case, we would lose some kind of energy. You could say we are not losing energy, but energy would be transferred from the positive side to the negative side, letting us lose charge overall in the process. But with this dielectric material in here, what is going to happen? You are going to notice that now overall, this dielectric material is going to be charged positively on this side and negatively on this side overall. This is just a simplification. You see positive and negative here in the whole dielectric material. Meaning what we got is we got an opposite electric field to the electric field inside of the capacitor that we got here. Meaning it's just like if the electric field in here from the capacitor would amount to a number of 5, okay? Then this opposite electric field that we got inside of the dielectric would amount to -4, okay? If we speak in terms of vectors. I just want to simplify this a tiny little bit. So the overall electric field, the resulting electric field inside of the capacitor is going to amount to 5 minus 4 equal to 1. So we're not going to lose any kind of charge in here, and this is the main role of the dielectric material. the better the dielectric material, better means the higher the permittivity, I think it's in English, the more charges we can keep inside of our capacitor, letting us store more energy, charges, voltage, etc. in the process. It's a very cool thing, and I hope I explained everything correctly. Andrew, please don't slap me if I got anything wrong. Okay, I'm a theoretical physicist overall, not an experimental physicist, but this is how I understand capacitors at this point. And this was just a tiny little overview, and now we are going to go over to the experiment and see what this is all about. Now, in my worksheet, we have a circuit given that my students are going to use in the later part of the experiment. You can download the whole worksheet. It's in German though, from ResearchGate down there, link in the description, and take a look at it yourself. But what about the first part? The students don't know much about the capacitor yet. The first thing that they are going to do is they are just going to put the capacitor in series with our transformator we've got right here with the electric source. And then in parallel, they are going to put the voltmeter to our capacitor to see how the voltage is going to act. That's the first part. Now this is exactly what I was talking about earlier. If you charge a capacitor, it's gonna keep that charge, just like a battery. The voltmeter was showing us that even if we turn off our electric source from the capacitor, we are still keeping a charge in here, a voltage in some kind of way. And for this part, they also need to draw down the circuit plan. That's like the last thing they need to do next to putting everything down. They are going to observe. And now we are going to get into the fun part. At the start of our worksheet, they have seen the circuit plan. So they need to now construct the circuit plan with exactly one resistor of 1 kilo ohm in resistance. The special thing about this is if you were to just put the resistor and also the capacitor in series and not parallel, what is going to happen is that if you charge the capacitor and then uncharge it or turn off the switch, I would rather say, then it's not gonna uncharge at all because resistance is futile if you have it in series with one other element here. So what we need to do is we need to put the resistor in series with the rest of the circuit, but then we need to take the capacitor and we are going to put it parallel to our resistor and then also our voltmeter parallel to the whole thing. Students are gonna charge once again the capacitor. As observed before, we can store energy in here, and then they are going to turn off the switch. And what they are going to notice is that the voltmeter is going to drop at the very start very rapidly, but till the very end, up until 0.2 volt, it's gonna slow down tremendously. And I'm going to give my students a hint and say, film all of this with a camera, because then you can better see all of your results. And for each and every passing second, they need to use Excel and write down all of the voltages that come with it. Because what you want to do is you want to draw out in Excel the discharge curve of the capacitor, meaning we are going to plot the voltage with respect to time in there. Once they are done with 1 kilo ohms of resistance, they are going to put one more resistor in to amount to 2K overall. That is very nice, right? 1 plus 1 makes 2. Quick maths. To do that, all you really need to do is to just put another resistor in series with the other one, and then we are going to repeat the experiment. Film the whole thing. For each and every passing second, you are going to note which voltage you still have in your capacitor. Once you're done with that, you are going to do it with 3 resistors, amounting to 3K in resistance overall. And then repeat this one once again. What you're going to notice too is the higher the resistance, the lower the stored voltage on your capacitor is. This is just something that you can obviously observe. And once they are done with that, there are 4 more tasks that they need to do. The first thing is they need to explain, before doing anything really in Excel, how the voltage is going to act with respect to the time that has passed. I want them to note something of the sort that obviously it's going to be a discharge of the capacitor. So our voltage is going to get lower as time passes. But what they also need to note is that at the start it's going to go very fast, it's a pretty quick boy, but at the very end it's going to slow down tremendously. And maybe they can already tell me, I think this is task 2. No, it's actually task 3, but maybe they can already tell me what mathematical function this could imitate or maybe follow after. If we take a look, soon in Excel, you are going to notice very quickly what it looks like. And if we put a regression or trend line into there, it becomes even more apparent. Next, one very important point is which correlation does exist between the amount of resistance you have in series with your main circuit and the discharge curve of your capacitor. It's very noticeable, but the higher our resistance, the slower it's gonna discharge. This becomes really apparent if we take a look at the corresponding function. And the last part is, after they have plotted everything in Excel, what does the regression curve look like? And if that regression curve fits their initial assumption about the mathematical function that they assumed this capacitor discharge to imitate after. And that's basically everything they need to do. I would like to get into a bit more detail about the discharge curves and everything, but before we can get into that, I need to go through the whole experiment here. And also I need to plot everything in Excel. It's gonna be a live thing, okay? I'm gonna do it right in this video. I haven't prepared anything, but I wanna see if it works out because of tomorrow, where they need to do it. So it would be cool if everything worked out such that they can kind of get the same results as I do. So let's not waste any further time. Now, don't you think that this is really cool? All of those curves follow an exponential regression. And with this information, we can actually get into a bit more mathematics during the physics class too. We are not covering differential equations in just regular physics classes. But what we can do is, through this experiment and the things that they can see in the regression, we can assume the process to be of exponential nature. And if we assume it to be of exponential nature, our corresponding function is going to be of the form t times a to the x power, where a is a certain base and t is our starting value, basically our y-intercept. And in class, I can go ahead and derive all of this with my students, and we're going to do exactly this over on the chalkboard. Alright, as always during experiments, and if I talk about those in class, I'm going to use the results that my students got to derive things, because this way they are going to feel very valued, at least I do think so. If your stuff gets featured in class, then that's pretty cool, I suppose. So let's suppose those are the results that my students get. And U0 is the voltage at the point t being equal to 0, and U1 is the voltage at t being equal to 1. We only need two values or pairs of values to define ourselves the exponential function. No need for differential equations here. We can observe in Excel that it's an exponential behavior. Most certainly, it looks like it, the regression fits. So we can go ahead and get started. This is how a lot of physics is actually happening. If you don't know about shit, then you're going to plot it and then you're going to see what the regression best fits. And then you're going to make an assumption, well, it's of polynomial nature, or in our case, exponential nature. So as mentioned before, we are going to define our function with respect to t as follows. Overall, it's the voltage with respect to t. So instead of f, we are going to take u of t. Is of the form, let's say just n times a to the tth power. Now we can plug our values in. If we plug u naught in, then we are going to get 4.4 is equal to, if we plug t being equal to 0 into here, we are going to get n times a to the 0th power is just n. As mentioned before, for the exponential function, our starting value is going to be our y-intercept overall, so n. So u of t for the first one is going to be of the form 4.4 times a to the tth power. And now we can plug our next value in. For t being equal to 1, we are going to get a value of 3.8. That's the equation that we need to solve. A to the first power is just a. So now dividing both sides by 4.4 is going to give us a base of our exponential function as being 3.8 divided by 4.4. Leave it as it be. It really doesn't matter right now. And now what we can do is we can plug our base into here once again, giving us an exponential function u of t for our first curve as being of the form 4.4 times 3.8 divided by 4.4 to the tth power. This right here is our first exponential function. And it's very easy to derive for the other ones what they should be. So the next one is going to be, I'm going to call this u. That was for a resistance of 3000, so I'm going to call it U3. This right here is U2. It's going to be, so our starting value is 6.65 times, and then we are going to get 5.75 divided by 6.65 to the tth power. And U1 for 1K of resistance is going to be 9.6 times 8.4 divided by 9.6 to the tth power. And those are our three exponential functions, which make up basically our whole experiment. But before we end the video, I would like to go one step further here. And for this, I'm just going to pick one of those three. It really doesn't matter. There would also be further exploration for the students. Now, this exponential function right here, yeah, it does work out, that is nice, but in a normal case, what you like to do is you like to write everything in terms of the natural exponential function, so with Euler's number as the base. So let us rewrite this one right here. It's going to result in 6.65 times e to the natural log of what we got right here. We can bring the t to the front, t times the natural log of 5.75 divided by 6.65. Now what you are immediately going to notice here is that the argument inside of our logarithm is less than 1. Meaning what we are going to get is a negative number of sorts. So u2 of t is going to be of the form 6.65 times e to the negative blah 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 t. Now, if we take a look at the capacitor, wherever it is right now, a capacitor, as the name suggests, has a certain capacity. The students know about capacity already. Capacity is the amount of charge you can store inside of this thing, and this capacitor has a capacity of 4,700 microfarad. Now micro means 2 and 10 to the negative 6, so 4,700 times 10 to the negative 6 farad. And we were using the same capacitor on all of these experiments. So this right here is a fixed value. And the capacity obviously plays a role when it comes to the charge or the voltage which is being stored inside of the capacitor. So this part up here has something to do most definitely with the capacity. But there's another thing that plays a role, namely the starting charge or the starting voltage on all of those exponential functions is always a different one. What we have noticed is that the exponential decrease basically is gonna be different for all of those. They all take around 23 seconds to reach from their initial values around 0.2 volts overall. So meaning what we got up here is most definitely dependent on the amount of charge you can store in there, so the capacity in some kind of way, and also it's dependent on our resistance in some kind of way. What I would do with my students is I would like to calculate the value of the natural log that we got up here. And the value of the natural log that we are going to get is roughly 0.12. This is what we are going to get, negative 0.12, because of the natural logarithm. Now, let us take a look at the capacity and our resistance. In this case, we got a resistance of 2000 ohms. If we got a resistance of 2000 ohms and we multiply it by 4,700 times 10 to the negative 6 farad. And if we then take the reciprocal of this, so 1 divided by 2000 times 4,700 times 10 to the negative 6, what we are going to arrive at is, we got a negative sign right here, okay, 0.16 up there in our exponential function. So by trial and error and talking about what this part up here can depend on, students might be able to see that this part that we got right here is going to be the same as 1 divided by R times C, resistance times the capacity. But this is a harder process, and this is a process that is being followed up by me. I'm going to explain to the students why this is the case, but we are going to back everything up with calculations and the things that they have found out during their own experiment. And this is indeed the exponential function that is going to guide the voltage. Namely, U of t is always going to be U naught, so the voltage at the start times e to the negative 1 divided by R times C, and then times t. And this right here is the solution to the differential equation, and it can be found out empirically by doing the experiment. And the same rules hold also for I with respect to t, just with I naught instead of U naught, and also Q with respect to t, where Q is the charge inside of the capacitor. And this is about it. And there's a lot of things that can be discovered with this simple experiment and with playing around with the resistors and the like. And I hope you did enjoy today's video. It wasn't about fundamentally understanding something in physics, it's about trying around. Physics is a black box. If you do experiments, you can find out something about nature and the behavior of, for example, capacitors. And maybe this gave some insights to you, and I hope you did enjoy what you have seen today. And if you did, make sure to subscribe to the channel for more advent calendar content and everything of that sort. And up until the next video, actually guys, Flammy day. See ya!